So what we're going to do now is we're going to take a little bit of a step back into the mid-19th century where we've gone through and discovered many different elements, but rather than just kind of organizing them alphabetically or organizing them based on their relative mass, we want to try to organize them in a way that represents their reactivity with other materials. And in 1869, Dmitri Mendeleev designed the periodic table, the basis of the current day periodic table we use today, by arranging elements in increasing atomic mass with elements with similar properties repeating in columns. So if we take a look at the periodic table on the right-hand side here, you'll notice that if you go left to right, the elements increase in mass very similar to how elements increase in mass on our current day periodic table. So you look at lithium, which has a mass number of 7, beryllium 9.4, boron 11, carbon 12, nitrogen 14, etc. And if you look at the second row on the periodic table, you see something very similar where it goes lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, etc. Notice he didn't just continue moving forward and just continue them in a line here. He stopped and then restarted with a new line, a new row, if you will, and then repeated this process over and over again. Well, how did Mendeleev know to go through and do that? Well, it all depends on the reactivity with oxygen. So for example, if we look at the top part where it says group 1 and underneath that it says R2O, what that means is that everything in that column reacts with oxygen in a 2-to-1 ratio. So for example, hydrogen reacts with oxygen to form H2O. Lithium reacts with oxygen to form Li2O. Sodium reacts with oxygen to form Na2O, and so on as you go down the group. And what you notice is if you look at the current day periodic table, the group is relatively unchanged. There are a few elements that are in there that do not belong for a variety of different reasons, but they also reacted with oxygen in the same way. In the second group, very similar, you see RO, meaning that that particular element or the elements in that group react in a 1-to-1 ratio. So beryllium and oxygen would be BeO, magnesium and oxygen, MgO, calcium and oxygen, CaO, etc. And if you look at the second group on the periodic table, you see something, again, very similar. Now, again, there are some elements there that don't belong for a variety of reasons. One thing I want you to notice is if you go down the group that starts with silicon, and you see silicon, and then you see a blank, and then you see SN, and then you see PB. So I'm in group number 4, and on the right-hand side of group number 4, you see Si, which is 28, and then you see a blank space where there's 72, and then down below it you see SN at 118, which is 10, and below that PB, which is 207. So Mendeleev not only mapped the periodic table, but this is what's really amazing about his work, is that he left a spot on the periodic table that there wasn't quite an element that fit that particular pattern. And what he did is he left a spot blank, stating that there is an element there that has yet to be discovered, and that is actually the case. Germanium now fits there, which had not been discovered during the time in which Dmitri Mendeleev built the periodic table. So not only is it organized in a very similar way that our current periodic table is organized, but he was also smart enough to know where to leave spots and blanks for elements that had not yet been discovered. How cool is that? Pretty neat. But this is the basis of the modern day periodic table. The first thing we're going to define are periods, which are the horizontal rows of elements that are on the periodic table, and these are represented by standard numerals. So if we look on the left-hand side of the periodic table, you see period, and then you see 1, 2, 3, 4, 5, 6, and 7. They go across the periodic table. Please make note that there are purple elements down at the very bottom. So notice in period number 6, you have 55, 56, 57. It jumps down to 58 through 71. Those first group of purple elements, the top row rather, is in the 6th period on the periodic table. And then the one underneath it is in the 7th period on the periodic table. Big reason why we do that is so that way all of the elements actually fit on a standard 8.5 by 11 sheet of paper. And then our groups, which are inherently more important than knowing the period number, our groups are vertical columns that are on the periodic table. Sometimes they're referred to as families as well. And these are Arabic numbers and Roman numerals. So you see group 1A, group 2A, you see a bunch of group Bs, and then it's 3A, 4A, 5A, 6A, 7A, and 8A, or group 1 through 18. Either way is perfectly fine. But there are 4 common groups of element names or names of groups that you're going to need to know for this particular course. The first group I'm going to want you to know are the alkali metals, and this is the group that is on the far left-hand side of the periodic table. The alkali metals are the general name for the first group, group 1A on the periodic table, and they're named so because when they react with water, they typically form substances that are basic in nature. These are soft, shiny, readily react with water. The lithium is something that you can actually really take and cut with a plastic fork. It's very, very soft and easily break apart, but it readily reacts with water. You've probably seen videos on YouTube of people taking lithium, sodium, potassium, things like that, dipping it in water and watching the reaction take place. Quite violent. The next group over is the alkali earth metals, and this is the general name for the second group on the periodic table. We'll refer to that as 2A. And they're similar to alkali metals, but they're less reactive with water. You do find these often in the earth, hence the name alkali earth metal. So first two groups on the periodic table you are going to need to know the name for. Our last two groups on the periodic table also have very important names. The first one is group 17. That is the second to last group on the periodic table, and those are known as halogens. The term halogen literally comes from the term meaning salt forming. And these are typically room temperature gases that are quite reactive, things like fluorine, chlorine. Bromine's actually liquid, iodine's a solid, but they tend to be quite reactive as well. And then on the far right-hand side, you have what are called noble gases, and that's the general name for group 18. These are very unreactive. And so what we can do is we can play basically a game of Battleship. If I give you a period number and a group number, you should be able to tell me the element that I am discussing based off of that's location on the periodic table, again, like a Battleship grid. So that being said, what I'd like you to do is to pause the video and take a few moments and go through and determine which element we are discussing based off of this descriptive information of its location on the periodic table. Take a few moments, work through that, and we will be back here in just a moment. So again, we're going to just utilize these like a battleship map, find period 3, go across until you find group 4A. You are going to be looking at silicon. The period 4 noble gas, all the way down to period number 4, your noble gases are group 18 on the far right-hand side of the periodic table. That's going to be krypton. Period 2, alkaline earth metal, we go to period number 2 and go across, we find that it is beryllium. And the period 3 halogen, again period 3 all the way across chlorine is going to be the period 3 halogen we're looking at. So again, just utilize this like a battleship map and it should be fairly easy to go through and tackle. So again, we will look at the spacing of the elements that are on the periodic table. You may find that the periodic table kind of jumps around a little bit, particularly if you're looking at elements 58 through 71 and 90 through 103. And we've just kind of snipped these out of the location where they would normally find on the periodic table and kind of dip it down to the bottom. Now you may notice that there are some places where elements jump here and there on the periodic table. That has to do more with the number of electrons that are in its outermost shell and the levels and sublevels and orbitals that those electrons exist in. Again, beyond the scope and sequence of this course, don't worry about it too much. If you are concerned about it, I have an electron configuration video that you are more than welcome to take a look at a little bit later on. So let's talk a little bit about some of the differences of the elements that are on the periodic table. And again, Mendeleev did this based off of how they reacted, but there are also multiple trends that are present on the periodic table that were kind of a happy accident in regards to how they were formed just based off of their reactivity. The first one we're going to look at is the difference between metals and nonmetals and their locations on the periodic table. Metals are elements that have luster, meaning that they are very shiny when you look at them. They're very good at thermal conductivity, meaning that they retain and conduct heat very, very well, as well as electrical conductivity. There's a reason that wires are made out of metal. In addition to that, metals are also very malleable, meaning that they have the ability to bend, flex, and you can mold them into certain shapes. And things like copper, zinc, lithium, silver, they're all considered metals. Nonmetals are elements that have no luster, meaning that they're very dull. They have no thermal or electrical conductivity, meaning that they don't retain heat or electricity very well, and are not malleable. They tend to be very brittle. These are things like sulfur, oxygen, fluorine, iodine. You can see on the right-hand side there, they're very much in their powdered form. They're not going to be able to retain electricity or heat. They don't have much luster. They're not flexible when you try to manipulate them. They just kind of break apart into much, much smaller pieces. Now, most elements on the periodic table are metals, and what I'd like you to do is notice the stair step that's on the periodic table. If you've not done so, go ahead and draw the stair step on your periodic table, starting at just to the left of boron, and just work a stair step down the periodic table until you get to the very end. Everything to the left of that stair step is considered a metal by definition, and everything to the right of the stair step is considered a non-metal. Now, there are some elements that are touching that stair step that are kind of exist properties that are metal and non-metal. Those are called metalloids. I wouldn't stress on that for this particular course. Just know that everything to the left of the stair step is a metal, and then everything to the right is a non-metal. So again, take a moment, pause the video. Based off of the information we just discussed, go through and evaluate your knowledge of the information we just took a look at. Take a few moments, thank you. So which of the following is a property of most metals? Most metals are going to be malleable. That means that they have the ability to bend and mold, and you can take them and put them into a variety of different shapes. Which of the following is a metal? We're looking for something to the left-hand side of the stair step on the periodic table. Again, that is going to be C. Now, the explanation for periodic law, the reason why that those particular elements bond in a certain way, has to do with the arrangement of the electrons that are found within an atom. Mostly the outermost electrons. These are the ones that are of most interest because these are the ones that are involved in chemical bonding. There are also electrons that are called core electrons that are not the outermost. These are the ones that are further inwards, closer to the nucleus. So while electrons are free-flowing and moving around the nucleus, some electrons are just naturally further away from the nucleus than the others. These are the ones that are going to come in contact with other elements that the chemical's trying to bond with, and those are the ones that are going to interact to create chemical bonds. Core electrons are the ones closer on the inside. You can see that we're utilizing the Bohr model here with the rings. We know that that's not fully an accurate representation of the model of an atom, but the ones that are on the outside are the ones that are most likely to interact with other elements, while the ones that are on the inside aren't going to interact with other elements. So being able to determine the number of core electrons and the number of outermost electrons actually becomes quite important, because that gives us an indication of what types of bonds can be formed based on the number of outermost electrons that different elements have on the periodic table. So valence electrons is another term for the outermost electrons of an atom, and the number of valence electrons in an atom is solely dependent upon its location on the periodic table. It's a periodic property that really helps explain the reactivity that Mendeleev was seeing when he went through and designed the periodic table. And as you see here, it's very, very simple to determine the number of valence electrons that are present in a given atom. In the very first group on the periodic table, each of those elements has one valence electron. In the second group, 2 valence electrons. We skip all of those ones that are in the middle there, and we go to group 13, which has 3 valence electrons, 14 has 4 valence electrons, 15, 5, 16, 6, our halogens have 7, and our noble gases have 8. So if we know the element in question and we know the number of valence electrons, we can figure out the number of core electrons, because the total electrons is going to be the core electrons plus the number of valence electrons. We can do a little bit of math and figure out how many core electrons an element is going to have based off of its valence electrons and the total number of electrons it has. So, as I mentioned before, the first column has 1 valence electron. All other electrons are considered core. The second column has 2 valence electrons. All other electrons are considered core electrons. And the trend continues through your main group elements. That is, the ones that are not the shorter groups that are found in the middle of the periodic table. So let's run through an example. Calcium has 20 total electrons. We know that based off of its periodic table location. We know that calcium has an atomic number of 20. Remember that the atomic number is equal to the number of protons, which for now is also equal to the total number of electrons it has. There are 2 valence electrons, so the remaining have to be core electrons. Well, if there's 20 total electrons and 2 are valence, that means that 18 have to be core electrons. So based off of the information of the location of the element on the periodic table and the relative number of valence electrons, you should be able to determine the number of core electrons that are present. So the next thing I want you to do here is to determine the number of core electrons and valence electrons that are in the following elements. Take a few moments and we'll come back and finish up our discussion for this evening. So starting off with bromine, if we look at bromine's location on the periodic table, we find that it has 35 total electrons, and based off of its periodic table location, it also has 7 valence electrons. So the number of valence electrons plus core electrons will equal the total number of electrons, so therefore there has to be 28 core electrons. Boron has a total of 5 electrons. It has 3 valence electrons based on its periodic table location, so it has to have 2 core electrons. And then lastly, neon has 10 total electrons. It's in the noble gas column with 8 valence electrons, so therefore also has 2 core electrons. So again, pretty easy to figure out based off of its periodic table location, its atomic number, and then you can very easily determine the number of core and valence electrons based off of that information. So the last couple things I want to go through and discuss for this evening is that elements can be classified based on their electron configurations. That is, the information that we get from how many outermost electrons they have tells us what type of element it is. And I go back and talk about the noble gas elements that are on the far right-hand side of the periodic table. They're unreactive because they have a full outer shell of electrons. You may be familiar with something that's called the octet rule. Now, that's not familiar with it. We'll talk more about it when we get to bonding, but most elements are most stable when they have 8 electrons in their outermost shell. And all the noble gas elements that are on the right-hand side of the periodic table have 8 electrons in their outermost shell. The only exception to that is helium, and helium only wants to have 2, and therefore, because it's the second element on the periodic table, has 2 electrons in its outermost shell. That provides us with an explanation as to why they are so unreactive, is because they have no desire to either take in or give up electrons in order to bond with other elements on the periodic table. A couple of other terms I want to make sure that you know. Representative elements, sometimes these are referred to as main group elements as well, are located in the first 2 columns, and then the other 6 columns for the representative elements are on the right-hand side of the periodic table. Transition elements are the ones that are in between the 2 groups of representative elements. These are things like scandium all the way to zinc. You have 10 groups that are there that are transition elements. Intertransition elements are the ones that are located on the very bottom part of the periodic table. They're the ones that we kind of snipped and took out and replaced down at the bottom. You may see like the continuity error going from 57 to 58. 58 through 71 is represented on the bottom of the periodic table, along with 90 through 103. So again, based off of this information, we should be able to very easily tell locations of elements, playing sort of a battleship style game. What is the noble gas found on the 3rd period of the periodic table? The 3rd period is that sodium period going across, and then the noble gas that's going to be found there is going to be argon. The alkali metal in the 4th period, again, alkali metal is that first group on the periodic table. 4 periods down, you're looking at potassium. So that pretty much rounds up everything we're going to be taking a look at for tonight. I really hope you enjoyed the video. I hope this helped explain a variety of different things, including how we determine the number of protons, neutrons, electrons in an element. Also hopefully helped you determine the average atomic mass, the design of the periodic table, and how we go through and identify elements based off of their location, as well as some of their properties. So hopefully you liked the video. If you did, make sure you give it a like, subscribe if you're interested for learning more, and thank you so much for watching for today. We'll see you very soon. Bye.